All right, so let us talk about the usual rules for domains of functions. I will first off start by saying there are a couple other tiny little things that occasionally come up for functions that have strange domains. Mostly it's for inverse trig functions, but generally, if someone asks you about the domain of a function, there are three things you need to consider. Are you maybe dividing by 0? We don't want to do that. Are you maybe taking the square root of something or an even root? Right? Odd roots are okay. You take an odd root of anything, but you can only take an even root of a positive or number or 0. So you can't have any negatives here. And for logarithms with any base, you can't take a logarithm of something that's 0 or negative. So if you have division, we usually say the denominator, we want to exclude where the denominator is equal to 0. If you have a square root or any even root, you want the stuff inside the square root to be greater than or equal to 0. And if you have a logarithm of some stuff, you want the inside stuff to be strictly greater than 0. So those are the three domain things you always want to think of if someone asks, what's the domain of this function? Do I have division? Do I have a square root or an even root? Do I have a logarithm? If any of those things are present, you might have a domain restriction. So let's look at some examples. Let's look at these three functions, which have sort of the same issue. Yes, I see you back there, Kat. So let's look at this first one. If I wanted to find the domain of f of x equal to 6x plus 1 over x squared minus 3x minus 10, I know I need to exclude where x squared, not x cubed, x squared minus 3x minus 10 is equal to 0. We're going to factor. This factors is x minus 5 times x plus 2 equal to 0. And then we're going to set, well, we're going to solve, right? We're going to get x equal to 5 and x equal to negative 2. You don't need to draw the number line. I kind of like to. So I draw the number line. Right, there's negative 2, there's positive 5. I only care about putting those numbers on the line. I don't want negative 2 and 5, but I do want everything else. So I want all of this, I want all of this, I want all of this. So that's going to be everything from negative infinity to negative 2 exclusive of negative 2, and then negative 2 to 5 exclusive of both 2 and negative 2 and 5, and then everything from 5 to infinity. On the other hand, let's try this one. So for this one, it's going to be the same sort of thing, except instead of setting the insides of this equal to 0, we're going to say the insides have to be greater than or equal to 0. I'm going to go ahead and factor it right away. So we're going to say that x minus 5 times x plus 2 has to be greater than or equal to 0. This is where it's really actually vital to use the number line. So let's do it over here. So the same zeros are going on my number line, right? The things that make this equal to 0 are negative 2 and positive 5. But now I don't really care that it's equal to 0. In fact, I want to include the points where it's equal to 0. But I need to know which sections of this entire real number line are positive, or which values of x make this expression positive. So I'm going to pick different numbers. I'll pick something in here, something in here, something in here. Pick x equal to 7. 7 minus 5 is positive, 7 plus 2 is positive, and their product is positive. If I pick x equal to, say, 0, 0 minus 5 is negative, 0 plus 2 is positive, and negative times a positive is negative. If I pick x equal to, say, negative 4, negative 4 minus 5 is negative, negative 4 plus 2 is negative, and then negative times a negative is positive. So I want the sections where it's greater than or equal to 0. So all of this, I don't want any of this, and I want all of this. So my domain for this expression, this function, would be everything from negative infinity to negative 2 inclusive of negative 2, and then union 5 inclusive all the way to infinity. Now, the nice thing about a square root and a natural log, if it's a square root of something and the natural log of the same something, their domains are going to be essentially the same. The only difference usually is that you're not including endpoints for the natural log or log with any base. So if I say, well, here I want my insides, which again, this factors as x minus 5 times x plus 2. I want those insides to be strictly greater than 0. We can see from this work before that it's definitely positive over here, and it's negative here, and it's equal to 0 at -2 and 5. I don't want it to equal 0. So here my domain is going to be all of this, but exclusive of -2, and then all of this, but exclusive of 5. So I don't include those endpoints. So that's how we find domain of the 3, or I should say, those are the 3 different types of domain restrictions where you have to exclude something. Typically with a fractional expression like this, you're only excluding some finite number of points and you're getting everything else. Whereas with a square root or a logarithm, usually you're excluding a whole section, right? A whole interval of the real number line. We've excluded all of this from our answer. So yeah. The reason this came up is because people were asking about, there was 1 or 2 homework problems where we were asked to find the domain of some logarithmic expression. So I'm going to change them around just a little bit, but these are pretty much the same. Let's look at a couple of these. I want to find the domain of, say, f of x equal to the natural log of x squared minus 9. So again, we're going to do the same sort of thing. We're going to set the insides to be greater than 0. Now, a word of warning. There's 2 ways you can do this. One of them, to me, is safer. The safer way is to factor. So I'm going to factor this as x minus 3 times x plus 3, which is greater than 0. And then we do the number line thing. 3 and -3, right? -3 makes this 0, +3 makes this 0. Those are the zeros of this expression. Pick numbers in each section. Pick 4, positive, positive. Pick 0, negative, positive. Pick -5, negative, negative. So we want this section, we want this section. We don't want the endpoints. So my domain is everything from -infinity to -3, union 3 to infinity. And you can check this, right? Like if you plug in, say, 4, well, yeah, 4 squared minus 9 is 7. 7 is positive, we can take the natural log of 7. Or if you plug in -4, -4 squared is 16, right? It's positive 16. Minus 9 is still 7, you can take the natural log of 7. If you plug in something like between -3 and 3, like 2, 2 squared is 4, 4 minus 9 is -5, you can't take the natural log of a negative number. The other way you can solve this, you can still get to the right place, but you have to be a little bit more careful. So you could do it this way. Again, I don't recommend this, but some of you might prefer this. You can say, okay, I'm going to say x squared is greater than 9, and then I'm going to take the square root of both sides. So you take the square root of both sides, here's what happens. You don't get that x is greater than plus or minus 3. It's not right. Because then you're saying, okay, x is greater than -3 and x is greater than +3. So I'm getting like all of this, or maybe just all of this, but I'm missing out, right? Either way, you're missing out on this section over here, what you need. So here's what actually happens when you take the square root of both sides. So you take the square root of x squared greater than the square root of 9. Okay, what's the square root of 9? Well, let me stop you before you say anything. It's not plus or minus 3. The square root of 9 is just 3. Right? When we take a square root, we only get the positive answer. If you're solving an equation, like if you're solving x squared equal to 25, we get x equal to plus or minus the square root of 25. But the square root of 25 is still just 5. And we tack on the plus or minus because we know there's a positive and a negative answer. So the same kind of thing is happening here, except here's what's actually happening. Square root of x squared isn't just x. It's the absolute value of x. In fact, that's actually what's happening here too. You take the square root of both sides, you actually get the absolute value of x is equal to 5. And then if the absolute value of x is equal to 5, x could be positive 5 or x could be negative 5. Same deal here. The thing with this is that when you have an absolute value inequality, you can say, okay, well, this means that either x is greater than 3 or negative x is, I have to make sure I do this right. Yeah, negative x is greater than 3. So that's going to be x is greater than 3 or x is less than negative 3. Actually, when you multiply by negative, you change the direction of the inequality. So we still get the same results, but in my opinion, this seems like a lot more work. So I would really, really, really strongly encourage everybody to, if you're solving an inequality and you happen to come across something like x squared minus a square looking number bigger than 0, don't do this. Factor it, do this. It's going to be, I think it's going to be easier. I mean, you can do this. You're welcome to do whatever you want. But I think this is going to be the simpler way to kind of understand what's happening. Yeah, let's look at a few more examples. Yeah. So let's look at f of x equal to the natural log of, what have I got here? X minus 3 plus the natural log of negative x plus 4. Okay, so we have to deal with kind of each of these pieces separately. For this part here, we know that x minus 3 has to be greater than 0. So x has to be greater than 3. For this part here, we have that negative x plus 4 has to be greater than 0. I personally, instead of so you could do this, negative x is bigger than negative 4, and then multiply both sides by negative 1 to get x is less than 4. But you can also just add x to the right and say, oh, 4 is bigger than positive x. Same thing, just written differently. So we need x to be bigger than 3. We also need x to be smaller than 4. So that's our answer. X is between 3 and 4. I guess what I'm trying to say here, right, is that you have to meet both conditions, right? You can pick something bigger than 3, like 5. 5 minus 3 is perfectly fine. But if you put 5 in here, negative 5 plus 4 is negative 1. We can't take the natural log of a negative number. So 5 doesn't work here. Similarly, you can pick something smaller than 3, like 2, and negative 2 plus 4 is positive 2, which is perfectly fine to take the natural log of. But you can't plug in 2 here because 2 minus 3 is negative. So we have to meet both requirements. So our domain is just the stuff in here. So our domain is everything from 3 to 4. What else I want to say about this? No, not really. Sorry, I'm just trying to think about one thing real quick here. No, yeah. Please do let me know if you have questions, right? I can talk about all the things for a long, long time, but if you have things you want me to talk about, I will definitely get to them. Let's do one more of these because there's one more. Let's say let's change the base. Changing the base actually doesn't affect anything. So, right, if this had been, instead of natural log, this had been log base, say 2, and this had also been log base 2, or even a different base, wouldn't matter if they're different bases. You still have the same domain restriction. You still have to have the insides bigger than 0, and the insides bigger than 0. Doesn't matter if your base is 2 or 1,000,000 or 5 or whatever. Look at one more example. So here, this last one, and again, I've changed it up a little bit. Let's say our function is log base 3 of 6 to the x. Where'd you go? Sorry, 6 to the x plus 1. So here, same domain issue. We have to ask ourselves, we have to set the insides to be, be greater than 0. There's a couple ways to do this. You can try solving for x, but the easiest way to do this is to say, well, look, we should know that 6 to the x already is greater than 0. That is a true thing, right? And again, kind of to go back, you're graphing exponential functions. If you graph something like 6 to the x, it looks like this. Has an intercept at 0, 1, has another point at 1, 6. Right? Every exponential function that has a base larger than 1 has this shape. If you pick a different base, it's going to look similar, but a little bit different. Like if I graph instead, let's say, I don't know, let's graph 3 to the x. Oops, no, that's fine. Yeah. 3 to the x might look more like that. It's where you have the point, 1, 3 instead of 1, 6. So all these exponential functions have the same sort of shape, just a little bit different from each other. But importantly, they're all always positive. And so if 6 to the x is always greater than 0, then 6 to the x plus 1 is greater than 0 plus 1, which is definitely greater than 0. So this is always true, which means it doesn't matter what x is. X can be anything, and this still works. So that means our domain is everything. You can either write the interval from negative infinity to infinity, or you could write the set of all real numbers. Either way would be fine. Yeah, if you wanted to, I mean, you could try solving this. You could say setting 6 to the x equal to -1, but then you're like, then take the log, right? You could say log base 6 of -1. Oh, that's a problem. We can't take the log of -1. So this having no solution kind of means we should go back to what we did before, right? There's not really a good way to work with it that way. I suppose, no, that seems like too much work. I was gonna say another way you could find the domain is to find the range of the inverse function, but that seems like a really complex, not necessary way to do it. So that's what I would say about these ones. Yeah. Sure, let's look at some other stuff. People had questions about logarithmic graphs as well, and how to shift them around. So let me take a look real quick here. Yeah. All right, one sec. I'm trying to see the various things. Sure. All right, that's what the first said. Try. I wrote down some notes here. So shifting log graphs. There's a few things we can do. Again, the general shape. If you're going to graph, say, either y equal to log base 2 of x, or in red, we'll do the natural log of x. They have the same general shape. They all intersect the point 1, 0. And then nat log base 2 of x, you'd also get the point where x is 2 and y is 1, when x is 4 and y is 2, and when x is 8 and y is 3, and when x is the next power of 2 and y is the next value. So looking like this. And then the natural log of x, a little bit less steep, right? Because instead of x being 2 and y being 1, you get x being, say, e, which is about 2.7, and y being 1. So it looks kind of like this. Same shape, though. Both have a vertical asymptote at the y-axis. Both have an intercept at 1, 0. Both have a domain that's all positive numbers, have a range that's everything. But then we might ask about like shifting them around. So kind of leave myself a whole lot of room here. Yeah, that was not the best. Well, let's say I want to graph y equal to, say, log base 2 of x plus 8, for example. Well, that plus 8 is going to shift it 8 to the left. So let's go ahead and erase this. We shifted 8 to the left. Well, the thing I think about when I'm shifting either logarithmic or exponential functions is if the asymptote's going to change. So if you shift the logarithmic function left or right, you are going to move the vertical asymptote left or right. If you shift it up or down, moving a vertical asymptote up, it's still a vertical line. It doesn't really move at all. But if you move that vertical asymptote left or right, it's definitely going to move. So if it was at x equals 0, we've shifted it 8 to the left. So now my new vertical asymptote is at x equal to -8, which makes sense when we think about the domain. If the domain of this function is x plus 8 is greater than 0, so x is greater than -8. And usually kind of like where your domain starts, right? We're starting right after -8. That value where you're not quite getting to is where your vertical asymptote is. And then, well, our intercept of 1, 0 shifted 8 to the left, so now it's going to be at -7, 0. And I've gone way too far down to start that. It's going to look like this. Now, if I was graphing this, I would also probably include the y-intercept. So I would set x equal to 0. And if x equals 0, then y equals the log base 2 of 0 plus 8, which is log base 2 of 8. But 2 to what power equals 8? Oh, 2 to the third power equals 8. So that's the point 0, 3. So that's one way we can shift a logarithmic function. I don't know. Let's see. I'm just trying to see if there's anything else to say about that, really. Yeah, let's do like maybe a couple more. So let's say I wanted to graph f of x equal to 4, yeah, sure, 4 seems terrible, fine. 4 minus the natural log of x. So first of all, this is written in kind of a not ideal way. I would probably rewrite it as the negative log of x plus 4. So that negative out in front is going to flip us vertically. So here's our kind of original natural log of x function. And then the negative in front would flip us over the x-axis. So instead of looking like that, it's going to look like this. Still the same x-intercept of 1, 0. And then this plus 4 is going to shift us up 4. So it's going to look like, and I would probably think about where this point landed. So I'm going to move this point up 4. So the graph is going to look kind of like this. And eventually it will cross the x-axis. Well, let's think about where it would cross the x-axis. So what's my x-intercept going to be? Well, if I set this equal to 0, right, that's how you find x-intercept, is setting y equal to 0. 0 is negative natural log of x plus 4. I'm going to add the natural log of x to both sides. Take the natural log of x equal to 4. And I'm going to e both sides. So e to the natural log of x equals e to the 4th. So x equals e to the 4th. Now, how much is e to the 4th? It's not small. One second, let me cat out of here. Yes, go ahead, you may leave. Oops. Okay, leave. Sorry. Calculator was a mess. Let's see, e to the 4th. Oh my gosh, come on. Is about 54. So I mean, right, that's my scale here, right? That's going to be, way out there. So if you graph this on like a graphing calculator, you might think You might fool yourself into thinking there's a horizontal asymptote somewhere because it looks like it kind of flattens out if you don't go up far enough. But eventually, this does in fact cross the x-axis, right? It's just hard to see it if you don't go up far enough. A logarithmic function never has a horizontal asymptote. Right? Always a vertical, never a horizontal. It keeps getting, right, going this way, it keeps getting larger and larger and larger. If it goes this way, it keeps getting smaller and smaller and smaller. Yeah. What else do people have questions about? I think there were some questions about solving exponential equations, and there were some questions about, oh yeah, also compressing logarithm stuff. And then also there was something else. Oh yeah, compound interest. We'll talk about some compound interest in a minute. So let's talk about expanding and compressing logarithmic things. So again, we talked about the logarithm rules a few days ago. And so often it's in our interest to either compress logs together or expand them. And we actually kind of talked about the expanding, right? So last class when I talked about say finding the derivative of something terrible like this. Right? The idea there is that we wanted to expand this expression because it makes it easier to deal with. So we can definitely write that as the derivative of the natural log of x squared plus the natural log of the square root of x cubed plus 1 minus the natural log of sine of x plus 2 minus the natural log of 2 to the x. And the way I encourage you to think about how you expand a logarithm of something complicated like this is any factors in the numerator end up with positive parts. Any factors in the denominator end up with negatives in front of them. And then you can also bring down the powers, right? You can write this as the derivative of 2 times the natural log of x, plus that's going to be a 1/2 power times the natural log of x cubed plus 1. There's no power here to bring down, so it's minus the natural log of sine of x plus 2. And then we can bring down the x here. And then we can differentiate. This is 2 times the derivative of the natural log of x is 1 over x, plus 1/2 times the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. So 1 over x cubed plus 1 times 3x squared. Minus the derivative of the natural log of sine of x plus 2 is 1 over that sine of x plus 2 times the derivative of sine of x plus 2, which is cosine of your stuff, times the derivative of the inside stuff, and the derivative of x plus 2 is just 1. Minus, remember I know we talked about this a lot, either last class or the class before, the derivative of x times natural log of 2 is just the natural log of 2, because the derivative of x times a constant is just 1 times the constant. And that would be your derivative. But the point of this is more that we are using the rules of logarithms to expand this expression to make it simpler to differentiate. However, sometimes it's in our interest to combine some logarithms together. Usually when you're solving like a logarithmic equation. So for example, let's say we want to compress into a single logarithm. I'm going to change this just slightly. 3 natural log of 4 minus 1/3 natural log of x to the 6th plus 10. So the way we're going to do this is we're going to first, so before you can put logarithms together, they have to have the same coefficient, and or the same, or opposite, meaning they can have a different sign. So now there's a couple ways to do this, which is always kind of problematic. I personally don't like to bring the negatives up into the powers. So I would prefer to write this as the natural log of 4 cubed minus the natural log of x to the 6th plus 10 to the 1/3 power. And then I would rewrite this, so I have a natural log minus another natural log. I can write that as the natural log of the argument of the first one divided by the argument of the second one. That's a perfectly good way to do it. That's the way I prefer to do it. However, you could also do it like this. You can say, I'm going to write this as the natural log of 4 cubed plus, I'm going to bring up the negative 1/3 as a power. The natural log of x to the 6th plus 10 to the negative 1/3 power. It's also a valid way of doing it. And then you could rewrite this as the natural log of 4 cubed times x to the 6th plus 10 to the negative 1/3. And then if you didn't want to have negative powers, you could rewrite this as the natural log of 4 to the 3rd stays on top. With this negative 1/3 power, we bring that whole expression to the denominator and we change the negative power to a positive power. And you get the same thing. Either way. Why do we do this? Why do we care? Well, again, occasionally we have to solve equations like, I don't know, okay, make something up that's not terrible. Sure. Let's say I want to solve log base 3 of, x plus 5 plus log base 3 of x minus 1 equals 3. And so to solve an equation like this, we really have to compress these logarithms together. We need to rewrite this as the log base 3 of x plus 5 times x minus 1 is equal to 3. And then we need to re-express this as an exponential equation. So my base 3 to the 3rd power equals this stuff in here. And then we try and solve this quadratic equation. So the 3 to the 3rd is 27. And it's equal to x squared plus 5x minus x is, well, let's just write it down. Plus 5x minus x, and then minus 5. It's bringing everything to the right. 0 on the left, I get x squared. 5x minus x is 4x. And minus 5 minus 27 is minus 32. This does factor. It factors as 0 equal to x plus 8 times x minus 4. And so in this case, we get x equals a negative 8 or x equal to positive 4. One other thing to be aware of for a problem like this is that sometimes some of your solutions aren't actually solutions. X equals 4, definitely a solution. If you plug in 4, 4 plus 5 is positive, we can take the log of a positive number. 4 minus 1 is also positive. So great, 4 is good. On the other hand, if you plug in negative 8 plus 5 is negative, and you can't take the log of a negative number. So negative 8 is actually not a solution to what we call an extraneous solution. You might wonder, why do we get extraneous solutions? And it's because if you look at this expression, negative 8 actually works out just fine. Negative 8 plus 5 is negative 3. Negative 8 minus 1 is negative 9. But negative 3 times negative 9 is positive 27. And log base 3 of 27 is equal to 3. So negative 8 is a solution to this equation. But if you look back at the original expression, it does not count as a solution because you can't plug in negative 8 here or negative 8 here. So that's what the issue is happening. That's happening there is. So yeah, expanding, compressing logarithms, something you want to definitely make sure you're able to do. In fact, I'm going to give you guys one to expand. So I want you to expand the following. I'm going to use the restroom real quick. So expand, sure, f of x equal to, what am I going to write? I don't know. The natural log of x cubed. Let's throw in some other variable. Sure, why not? W to the 6th over, sure, sine of x to the 4th plus 1 times, what else do I want? Sure, z to the 9th power. Go ahead and expand that. You should get 4 logarithms. I'll be right back. All right, so I'm going to show you an extra step that I probably don't usually do. So here's where I usually jump to. I usually jump to, this is equal to the natural log of x cubed plus the natural log of w to the 6th minus the natural log of sine of x to the 4th plus 1 minus the natural log of z to the 9th. If you don't like jumping straight to there, you can start with saying, well, I know that this is equal to the natural log of the top minus the natural log of the bottom. And then the natural log of x cubed times w to the 6th is this here. And I'm going to change this just slightly. I'm going to rewrite this as, instead of minus this and minus that, it's going to be minus the quantity this plus this. Because the minus sign distributes. And then you can see, oh yeah, that's minus this product, which breaks up as this plus this. And then the last step we should do is to bring down the powers. This is equal to 3 natural log of x plus 6 natural log of w. There is no power to bring down here because there isn't a power that's on the entire expression. This 4 doesn't get to come down. So minus the natural log of sine of x to the 4th plus 1 and then plus minus, right, because the minus sign distributes, 9 natural log of z. So that is how you would expand the logarithmic expression. And I know we've done a couple examples of that already, but worth showing you guys again. Okay. Let's see. Yeah, let's talk about solving some exponential equations, and then we'll talk about some compound. And then I think, well, if you guys have other questions, you're certainly welcome to ask them. I'm going to start moving towards talking more about doing a lot more derivative examples again. Yeah, we can do some implicit too. Yeah, maybe we'll do some implicit too. Anyway, right? There's so many, like this beginning part of 16b, there's kind of so many different things to talk about. So really whatever you guys want. I'm just kind of going through the list of what people ask me to do in the reflection. So that's what we're doing. Let's solve some exponential equations. So a lot of people ask me about solving something like this. It was something like the natural log of x minus 6 is equal to, I'm going to make it more interesting. Let's make it 2. All right. So the thing about this is it's not this. Right, that would be easy. E to the natural log of x minus 6 is just x minus 6. So x would equal 8. That's not what we have though. Right? If you have an expression that says e to the natural log of x minus 6, if there's not a parentheses, we have to assume that only the first thing that comes after the natural log is it's actually in the natural log. So it's e to the natural log of x minus 6 equals 2. Okay. I might have made this harder than it needs to be. That's all right. Sometimes things are hard. So if I was going to solve this, I would take the natural log of both sides. So I would say, okay, I have the natural log of e to the natural log of x minus 6 equal to the natural log of 2. And then we can, well, the natural log of e to a thing is just the thing. So that's going to be the natural log of x minus 6 is equal to the natural log of 2. And then we can add 6 to those sides. And that, I think the one, so, okay. I might have made this a little more difficult. The other one had a 1 there, natural log of 1, 0. Yeah, let me make it slightly easier so this looks a little bit more sensible. So in the homework problems, actually, there was a 1 there, and then this is the natural log of 1. The natural log of 1 is 0. And then we get the natural log of x equals 6. So solving for x, we get x equals e to the 6th. So that's what we end up getting here. Solving exponential equations like this is usually kind of a process of being able to go back and forth between writing it as something exponential and writing it as something logarithmic. Let me see if I can find a couple other examples. How would you, okay, sure, I can do those too. So if it was 2, it's just not quite as pretty an answer, but it's still perfectly fine. So I'm going to make it, let's say it's e to the natural log of x minus 6 equals 2. Same process. In fact, it's all the same process. It's just going to look less nice at the end. So take the natural log of both sides. So I get the natural log of e to the power is just the power. That's right. I took the natural log of the left, and I got the natural log of x minus 6. I took the natural log of the right, I got natural log of 2. Now I'm going to add 6 to those sides. So natural log of x equals 6 plus natural log of 2. And then I'm going to exponentiate both sides. So e to the natural log of x equals e to the 6 plus natural log of 2. You could leave your answer like this, but there's actually kind of a slightly nicer way we could write it. Well, first of all, this is going to be x, of course. Now, e to the 6 plus natural log of 2, you could leave it as is, but you could also write it like this. E to the 6 times e to the natural log of 2. And then e to the natural log of 2 is just 2. So you could write this as 2 times e to the 6th. And that would be a correct way of writing. That's probably considered the most simplified way of writing this answer. But the process is still the same, right? We're still taking the natural log of both sides, isolating the x, exponentiating both sides to figure out what it is. Yeah. Yeah, that was interesting. I like that. Let's do, yeah, of course, happy to, yeah, no problem. Always happy to answer other questions. Let's see, I was looking at the homework assignment to see if there are any other kind of remarkable looking exponential equations. I feel like I saw 1 or 2, but kind of hiding from me. Okay, yeah, there's things like that. Those seem not too terrible. Yeah. Let's go ahead and sorry, 1 sec. Okay, all right. Sure. All right, let's talk about compound interest for a minute. So you guys probably want to memorize the compound interest formula, at least for this if it's not being given to you. And the compound interest formula is the following. It's A of t, where A is the amount of money at time t, after, I should say, really. It's the amount of money after t years. And it's equal to the principal times 1 plus your interest rate divided by n to the nt power. Where again, your principal is the amount you're starting with. This can be either the amount you're investing or the amount that's being loaned to someone, right? Because a loan is just an investment from the person who's loaning out the money. N is the number of times we are compounding per year. R is the interest rate as a decimal, meaning if the interest rate is 8%, then it's going to be 0.08. Or if it's 25%, it's going to be 0.25. And finally, T is the number of years. I will also say there's an alternate version of this formula, which is that the amount of money after T years is equal to your principal times e to the RT. And this is specifically if you're continuously compounding. Or in other words, taking the limit as n, the number of times you're compounding, goes to infinity. So you take the limit as n goes to infinity of this expression, you get p e to the RT, which has to do with the fact that the limit as n goes to infinity of 1 plus 1 over n to the n is equal to e. Right, so that's how you get from there to there. I don't want to get too into it. I know I saw one of your teachers do it in class, so I think it's not super important to cover that specific aspect of things. But that's how you calculate things. And I will say most of the time with compound interest problems, it's usually just kind of throwing all the things you know into this formula and trying to find the thing they're asking you to find. So let's look at one or two examples. And sorry, let me give my examples here. Yeah. So, for example, here's this. So usually most of these problems are going to require some sort of calculator work. Suppose we invest $5,000 at 4% interest, compounded weekly. Not like week, but like every 7 days. How long will it take for our money to double? Okay, well, we know all the things that go into that formula, except for the one thing we're being asked for. We're being asked to find the amount of time. So I know that when I set up my equation, I should be able to substitute in for every other value except for time. So again, I've got right A equals P times 1 plus R over N to the NT power. I will also point out this question could have been asked without giving you a principal amount. Right? I could have just said, we're earning 4% interest and we're compounding the interest weekly. How long will it take for any investment to double? Well, right. Let me show you what I mean. So using the $5,000, here's what our equation looks like. We know that the amount of money after time t, which I'm not going to write because just wait, is going to be your initial investment, your principal, times 1 plus R. The interest rate as a percent is 0.04. Divided by the number of times we're compounding per year. Well, there's 52 weeks. We will not worry about the extra day or whatever that's in the year. Extra day in the non-leap year. So there's 52 weeks. So we're compounding 50 times per year to the 52 times t. Now we're asking how long it will take for the money to double. So that means we're asking, well, if I'm starting with $5,000, I'm asking how long until there's $10,000. And look, we filled in all the information in our formula except for the one thing we're trying to solve for at the time. But I want to point out that, well, let me do the first step to solve for this. I'm going to divide both sides by 5,000. So I'm going to get 2 equal to 1 plus 0.04 divided by 52 to the 52t. But I just want to say, right, if I just said I started out with any amount of money, so I started out with some principal times 1 plus 0.04 over 52 to the 52t. And I know I wanted to double my money, so I want to end up with twice my principal. If I divide both sides by p, I'm going to get to this equation exactly. So if someone's asking you a question about how long it takes to double or triple or multiply whatever you have by some amount, you don't actually have to know how much you started with. You can just make it whatever number you want. Because whenever you do this first step of dividing both sides by the initial amount, you're always going to end up with the multiplying factor over there. So either way, we're trying to solve this. I also want to point out that you should not use any decimal approximations until you're kind of at the very end. So like it's I've definitely seen people write out like, oh, 0.04 divided by 52 is some terrible decimal. 0.04 divided by 52 is 0.0007692, right? No, we don't want to write that out until we're actually trying to find our answer at the end. So I'm going to take the natural log of both sides. That's usually, like, you could use log base too, that would be fine. But it's usually more common to say the natural log of 2 equals the natural log of this hot mess over here, 1 plus 0.04 over 52 to the 52t power. We bring the 52t down in front. So the natural log of 2 is equal to 52 times t times the natural log of 1 plus 0.04 over 52. And then finally, we solve for this. So we divide by 52 and we divide by the natural log of 1 plus 0.04 52. So t is equal to the natural log of 2 divided by 52 times the natural log of 1 plus 0.04 over 52. And then if I was actually trying to see what that was using a calculator, right? This is the answer I would give if I was not asked to get a decimal approximation. If you want a decimal approximation, I would take this expression, natural log of 0.04 divided by 52. So let's see, 0.04 divided by 52 in my calculator, add 1, then take the natural log of that, then multiply that by 52, and then do the natural log of 2 divided by that answer. So that we're not like compounding our approximation, right? You don't want to approximate this and then approximate this, right? You want to just keep it all in the calculator until you get to the very end. So I'm getting about 17.3 years. Okay. Let's look at a slightly different take on things. Yeah, not that one. So most of the time, the questions usually focus around like, how much money do you have after so many years, or how many years until you have so much money? But you can also ask questions about like what the interest rate needed to be, or what the number of times you compounded per year was. So let's look at a question of that variety. So let's say we have, we're investing $400 into a savings account that compounds interest continuously. After 20 years, we have $2,000. What was the interest rate? Okay, well, again, we're just going to throw everything in formula. Now, the thing we have to remember here is that we're not using the compound interest formula. We're not using A equals P times 1 plus R over N to the NT power, because it's compounded continuously. So instead of this formula, we're using this one. The amount of money after t years is p times e to the rt power. We just got to fill in the blanks. We know the principal we're starting with is $400. We know that e is just the number e, it's 2.7-ish. R is what we're looking for. T is the number of years. And then A is the amount we have after those number of years, which is $2,000. All right, we can solve this equation for R. Divide both sides by 400. So 5 equals e to the r times 20. Take the natural log of both sides. The natural log of 5 equals r times 20. And so then r is going to be the natural log of 5 divided by 20. And then if you wanted a decimal approximation, we're going to get, let's see, the natural log of 5 divided by 20 is about 0.0804. So R is about 8%. That's our interest rate. I've got one other question here. I saw one on one of the homework problems. No, that's not really what I'm looking for. Never mind. Okay, so yeah, let's do one more because there are some. So the only question I haven't asked, well, not the only, but the style I see on some of, who is that? I think that's Ma's homework assignments. Ma's the one that has like the kind of the short ones, I think. He has like 4 assignments already, 5 maybe. Yeah, Ma's are those ones. Is how much money should you deposit with a certain amount of interest to have a certain balance later? So the question is, how much should we deposit into an account? Let's just make up some numbers. Earning 6.5% interest, compounded daily for 10 years to have, I don't know, to have $1 million at the end of those 10 years. Okay, well, again, throw it all into the formula, right? It's really just, here's a formula, put things in it, get things out of it. So let's see. We know that we want to have $1 million after 10 years. The principal is what we're trying to solve for. The rest of the formula is 1 plus my interest rate, which is 0.065, divided by the number of times we're compounding it, which is every day, so 365 times per year, to the 365 times 10 power. Well, this is actually very straightforward to solve for because we just divide everything by that. So the principal we're looking for is $1 million divided by 1 plus 0.065 over 365 to the 3,650th power. So plugging that in your calculator, again, I'm going to deal with the denominator part first. So I'm going to do 0.065 divided by 365, which is some dumb looking decimal. I'm going to add 1. I'm going to raise that to the 3,650th power. And then I'm going to divide $1 million by all that. So I got about 2. So it sounds like it's going to take a long time to have $1 million. Or no, we're going to have to invest a lot of money. Not a long time. It's going to be 10 years. So $1 million divided by that number, I'm getting $522,075. And 99 cents. So if you invested $522,075.99 for 10 years at this interest rate compounded daily, you would have $1 million at the end of those 10 years. So great. Whoops. So I think probably good. Let's go ahead and roll back around to derivatives, because although this compound interest stuff and like all these things are important, we're going to start moving towards the derivatives of all the things, and then we're going to start moving towards taking the anti-derivatives of all the things. And to be able to take anti-derivatives of things well, you really have to be very, very confident in your ability to differentiate everything. So let's look at some examples. Let's find the derivative of, and so actually I'm going to remind everybody, we know how to take the derivatives of exponentials and logarithms, right? We know the derivative of e to the x is e to the x. We know the derivative of some other base, a to the x is a to the x times the natural log of a. We know the derivative of e to something more complicated, like e to the f of x is e to the f of x times f prime of x. That's just the chain rule. And we know the derivative of a different base to some function is a to the f of x times f prime of x. That's the chain rule part. But then we also have to multiply with the natural log of your base, just like we do up here. And the logarithm rules are similar-ish. The derivative of the natural log of x is 1 over x. The derivative of some log with a different base, log base a of x, is 1 over x natural log of a. So what I always remember is if it's exponential and my base is different, you multiply by the natural log of the base. If it's logarithmic and the base is different, you divide by the natural log of the base. The derivative of the natural log of a function of x is 1 over the function of x times the derivative of that function, or as I like to say, 1 over the stuff times the derivative of the stuff. Just like the derivative of e to the stuff is e to the stuff times the derivative of the stuff. And then finally, the derivative of the log base a of some function of x is 1 over your function of x times f prime of x. And then we also have to divide by the natural log of that base. Which again, you could compactify this. You could make this look much nicer, right? It's like f prime of x over f of x times the natural log of a. So those are our rules for differentiating exponential and logarithmic functions. So let's look at some examples. Let's say we want to take, I don't know, the derivative of e to the 3x plus sine of x over e to the 3x plus cosine of x. That's going to be nasty looking, but fine. So taking the derivative to the bottom times the derivative of the top, which is actually this, well, almost the same. Derivative of e to the 3x is 3e to the 3x, or e to the 3x times 3. Can I go back, please? Sure. Yeah. No problem. Sorry, we have the chat kind of small here. Let me make it a little bit bigger so I can see it better. Yeah, there we go. Where'd you go? There was a problem I was looking for. Yeah, I can definitely. So sure. So you mean these last two ones here, Heidi? Definitely. So the only difference between these, so here's what I should really say. These rules are the same. It's just that this first rule is a special version of this second rule. I could throw in, sorry, I'm putting my pens in the wrong space. I could definitely put in a natural log of e there. It's just I don't need to, because now the natural log of e is 1. So whenever you're differentiating an exponential function where there's a chain rule thing, so if I'm differentiating a to the stuff, I'm always getting a to the stuff times the derivative of the stuff times the natural log of my base a. It's just that when it's e to the stuff, when you multiply the derivative of the natural log of your base e, you're going to get that's going to be 1. So we don't write it down. But they're actually really the same rule. The reason we have this here, the reason you have to multiply the natural log of a is because of, well, sure, let me show you. So here's where so if you're cool with the first rule, or not with this rule, if you're cool with the chain rule version of the exponential derivative, which is that the derivative of e to the stuff is e to the stuff times the derivative of the stuff, you can actually rewrite this using that. Meaning, I want to find the derivative of a to the f of x. I'm going to write this very generally. I'm going to rewrite it as the derivative of e to the natural log of a to the f of x. Right? We can always say, well, something is always equal to e to the natural log of that same something. And then we can bring this f of x down in front. This is equal to the derivative of e to the f of x times natural log of a. Okay, now I want to remind everybody, the natural log of a, if a is a constant, which a is supposed to be a constant here, the natural log of a is also a constant, like 7. So when I differentiate this, well, we know that the derivative of e to the stuff is e to the stuff times the derivative of the stuff. So the derivative of e to the stuff here is going to be e to the same stuff times the derivative of that stuff. Okay, the derivative of a function times a constant is the derivative of that function times the same constant. Just like the derivative of 7 times x cubed is 7 times 3x squared, which is 21x squared. The derivative of a constant times a function is the constant times the derivative of the function. The derivative of a constant times the function is just the constant times the derivative of the function. Okay, but now look, e to the f of x times natural log of a is the same as e to the natural log of a to the f of x, which is the same as a to the f of x. This part here is just a to the f of x. And that's where you get your formula from. There's another way to do this, but this is kind of the maybe easier way to see. Hopefully that clarifies things. So back to this. You're welcome, of course. I did the bottom times the derivative of the top, and the derivative of the top is going to be, so e to the 3x times 3 plus the derivative of sine of x is cosine of x. Minus, now we flip it, right? We do the, instead of the bottom times the derivative of the top, we do the top times the derivative of the bottom, which is going to be 3e to the 3x minus sine of x, all divided by e to the 3x plus cosine of x quantity squared. Generally, I would recommend against multiplying this out. I'm going to multiply it out here just because I want to show you that it does actually kind of simplify really. I made this problem up, but I can see there's a simplification here that I want to make you aware of. One reason is that if you're doing this problem and you look like in the back of the book to see the answer, you might not see this answer. You probably won't see this answer. You'll see the very simplified answer. So you do kind of have to be aware of how things simplify if you want to check your answers. So let's multiply this out real quick. E to the 3x times 3e to the 3x is going to be 3e to the 6x. Because e to the 3x times e to the 3x is e to the 3x plus 3x, which is e to the 6x. And then this times this is going to be e to the 3x times cosine x. This times this is going to be 3e to the 3x times cosine x. We can put that together and get 4 e to the 3x times cosine x. And then we're going to get cosine x times cosine x, which is cosine squared x. Minus e to the 3x times 3 to, so 3 e to the 6x again. And then we're going to get sine e to the 3x times negative sine, so minus e to the 3x times sine of x. And then sine of x times 3 e to the 3x, so 3 e to the 3x sine of x. And then sine times negative sine is minus sine squared x. All divided by the same denominator. Ugh, okay. It's kind of gross. But check this out. So here's what happens. 3 e to the 6x minus 3 e to the 6x cancels out. You can combine this as 4 e to the 3x cosine x. Okay, we're taking care of that and that. And then minus e to the 3x cosine x plus 3 e to the 3x sine of x is 2 e to the 3x sine of x. So it's minus 2 e to the 3x sine of x. Taking care of that and that. And then finally, a minus sine squared is a plus sine squared. So I've got a cosine squared plus sine squared, which is equal to 1, all over the same denominator. So this doesn't look nice, but it is worth pointing out that it does simplify quite a bit. Again, generally, I wouldn't worry too much about the simplifying, but sometimes you will have to simplify stuff. Oh, it's almost time to be done. Let's see. There was one other one I really wanted to hit. I don't remember what it is, so I'll just make one up. So I want to find the slope of the line tangent to the following equation. E to the x cubed y plus the natural log of x plus y equals x cubed plus 1 at the point 0, 1. Okay, so I want to find the equation of the tangent line. And if your equation is written like this, where you've got x's and y's mixed together, the assumption is we have to use implicit differentiation to find the derivative. So I'm going to differentiate this thing. Okay, so what's the derivative of e to the stuff? Oh, the derivative of e to the stuff is e to the stuff times the derivative of that stuff, which I'm just going to write as x cubed y for the moment. And I'm actually going to change this to y squared just to make it a little more interesting. Plus, the derivative of the natural log some stuff is, oh, sorry, I forgot something, right? It's e to the stuff times the derivative of that stuff. Okay, and then the derivative of the natural log of x plus y squared is 1 over your stuff times the derivative of your stuff. The derivative of x cubed, well, since we're talking about derivatives with respect to x, the derivative of x cubed is just 3x squared, and the derivative of 1 is 0. Okay, but now I have to actually go fill in the derivatives. Right, you don't need to do this in 2 separate steps. I'm just trying to do it in 2 steps to kind of show you the process. But you could say, oh yeah, I know the derivative of e to x cubed y is e to x cubed y times whatever the derivative is there. So here's what we're going to get. We're going to get e to the x cubed y. The derivative of x cubed times y, we have to use the product rule. It's 3x squared times leave y alone, and then you vice versa, right? Plus, now you leave x cubed alone, and you multiply by the derivative of y, which is the derivative of y. And the derivative of y is just the derivative of y. I know it's kind of weird, like, wait, oh yeah, right? It's just the derivative of y. You're just finding y prime or dy dx. And then we're going to get plus 1 over x plus y squared times the derivative of x plus y squared, which is 1 plus the derivative of some stuff squared is 2 times your stuff to the first times the derivative of your stuff equal to 3x squared. Okay, here's the thing to know about if you're finding the slope of a tangent line at a particular point. You don't actually have to solve this for y prime in terms of x and y. You can plug in 0 for x and 1 for y and then solve for y prime. That's actually going to make things a lot easier. If you're plugging in 0 for x and 1 for y, well, anything that has an x in it is going to go away. So let's see. 0 for x, that's going to be 0. 0 for x, that's going to be 0. That's this times 0 plus 0. This whole thing's going to be 0. This would actually be 1. But 1 times 0 plus 0 is 0. This might not be very interesting. I think kind of a lame answer here. Here I'm going to get 1 over 1 plus 0. So 1 times 1 plus 2 times 1 times y prime equals 3 times 0. Okay, so let's solve for y prime. Let's see. So 1 plus 2y prime equals 0. 2y prime equals negative 1. Y prime equals negative 1/2. So the slope of the tangent line at this point, 0, 1, is negative 1/2. And that's how you do a problem like that. So, one more examples of logarithms. Let's do one more logarithm, and then we'll call it a day. One more meaning, let's do one logarithm. And I guess on Thursday we will do more log and exponential derivatives, and then we'll also talk about logarithmic differentiation, where you can differentiate things like x to the cosine of x, and other weird, funky stuff like that. Well, let's find the derivative of, say, log base 3 of x to the 6th plus cosine of 7x squared. Okay, so derivative of log of a thing is 1 over the thing times the derivative of the thing, and then we also have to divide by the natural log of your base, which is the natural log of 3. So I'm going to get 1 over the stuff times the derivative of that stuff, which we can take right away, or we can wait a second. Let's go ahead and take it right away. So the derivative of this stuff, so the derivative of x to the 6th is 6 x to the 5th. The derivative of cosine of some other stuff is negative sine of that other stuff times the derivative of that other stuff, which is 14x. And then we also have to divide by the natural log of your base. And I would probably put this all together in one expression. I would write this as 6x to the 5th minus, I would probably write this part as 14x times the sine of 7x squared, all divided by x to the 6th plus cosine of 7x squared times natural log of 3.